2 episodes ago, we cataloged exactly how an attacker moves, stage by stage, using ATT&CK. Last episode, we found every individual flaw sitting in Kestrel's pre-breach design, one boundary at a time, using STRIDE. Neither exercise, on its own, tells you whether those flaws actually combine into a working attack. A system can have a dozen individually serious findings that never chain together into anything an attacker could use, or 3 seemingly minor ones that combine into a complete path to the exact thing you were trying to protect. Telling those 2 situations apart is what attack trees are for. An attack tree starts from a single root node, a specific attacker goal, stated concretely. Not get hacked, but something like exfiltrate patient billing records from Kestrel Health. Every other node in the tree is a way of achieving whatever its parent node requires, and the connections between siblings carry real logical meaning. An OR relationship means any one child is sufficient on its own. Several alternative ways to achieve the same thing. An AND relationship means every child is required together, a sequence of conditions that all have to hold. The formal notation was popularized by Bruce Schneier in a widely read essay at the end of the 1990s, building on fault tree analysis that safety engineers had already been using for decades to model how complex systems fail. The reuse is fitting. A fault tree asks how a system could fail on its own. An attack tree asks the same structural question about a system with an adversary actively trying to make it fail. It's worth being precise about how this differs from what we've already built this season. STRIDE asks, what could go wrong at this specific point? It's organized around locations in the system, each element and boundary analyzed on its own terms. An attack tree is organized around a goal instead, and shows every alternative and combined path to that one goal, using the individual flaws. STRIDE surfaces as the raw material that fills in its nodes. There's a natural extension worth knowing, even if we won't build one today. Attack defense trees add a second node type alongside attack nodes, defense nodes, showing which control neutralizes which specific attack node. Where a plain attack tree shows you the paths that exist, an attack defense tree shows you which of your actual controls sits against which specific path. A natural next step once the plain tree is built and you're ready to map your existing architecture against it, rather than just diagnosing where it's currently weak. Put the root at exfiltrate patient billing data from Kestrel Health, and the tree underneath it is built almost entirely from findings we already have. One branch of the root, connected by OR to whatever else sits alongside it. Compromise a contractor credential. That branch decomposes further by OR into a small number of ways to do it, phishing being the one that actually happened. Once that leaf is reached, reaching the goal isn't automatic. It requires an AND chain underneath it. The compromised credential has to actually reach the billing service, which requires the trust boundary gap we spent last episode on. No re-verification once inside the shared zone, and the data has to leave without triggering detection, which requires the missing request level audit trail, another one of last episode's findings, alongside the absent rate limiting on internal calls. Every one of those 3 and chained requirements is a specific STRIDE finding from last episode, and the tree is what shows they weren't 3 unrelated problems. They were 3 links in one chain, and all 3 had to hold simultaneously for the actual intrusion to succeed. There's also a second OR branch of the root worth drawing in, even though it wasn't the path taken, exploiting the public-facing application directly. Technique TR 190 from 2 episodes ago. It's a live alternative path in the tree whether or not anyone's used it yet, which matters for reasons the next scene gets into. Drawn out, the shape of this is simple. Even though the underlying logic is doing real work, a single box at the top for the goal, or connected branches drawn as separate lines fanning out beneath it, and connected requirements typically joined by an arc underneath a node to show they're bound together rather than independent alternatives. You don't need specialized software for a first pass. A whiteboard captures the structure perfectly well, and the and/or distinction is really the only notation convention that actually matters for the exercise to work. This is where the tree earns its keep, beyond just being a tidy diagram of what already happened. Or nodes mean an attacker only needs one path to succeed, so closing a single OR branch barely moves the needle if several alternative OR branches to the same goal remain wide open. And nodes mean every linked condition is required, so closing even one node inside an AND chain breaks that entire path outright, regardless of whether the other conditions in the chain still hold. Look back at Kestrel's tree with that in mind, and the priority becomes obvious in a way a flat list of findings never quite makes clear. The missing multi-factor authentication on contractor access sits at the top of an AND chain. Fix that one node, and the specific path the actual attacker used is broken completely, even without touching the missing audit trail or the absent rate limiting on the same path. That's not true of every finding on the list. A flat STRIDE findings list treats all of last episode's discoveries as roughly equal priorities. The tree shows you which one was actually load-bearing for the path that mattered. Worth placing one more model alongside this, because it's easy to conflate with what we've just built. Lockheed Martin's Cyber Kill Chain, published in 2011, describes intrusions as a fixed sequence of 7 stages: reconnaissance, weaponization, delivery, exploitation, installation, command and control, and actions on objectives. It predates ATT&CK and partly inspired it, and it's a genuinely useful lens, but it's a different lens from an attack tree, not a competing one. A kill chain tells you where you are on a shared timeline. Most intrusions roughly follow. An attack tree tells you which specific combination of conditions had to hold for one particular goal to be reachable at all. One is about when, the other is about which. It's worth naming a real limitation of the classic 7-stage model too, rather than presenting it as timeless. It was built around externally initiated, malware delivery-style intrusions, and it maps awkwardly onto exactly the kind of incident Kestrel actually had. There's no meaningful weaponization or delivery stage when the entire intrusion runs on a valid, phished credential rather than a delivered payload. Several of the 7 stages simply don't apply cleanly to valid account-based or cloud-native intrusions, which is a growing share of real incidents today, Kestrel's included. In practice, the two models are worth using together rather than picking one. A kill chain view helps you notice which stage of a generalized progression your detection and response capability is weakest at. Do you have anything that would notice reconnaissance? Or does your first realistic chance of detection sit at lateral movement, several stages in? An attack tree view helps you notice which specific combination of conditions, for one goal that actually matters to your organization, would make an attacker's job easiest. Run the kill chain lens across your whole security posture in general. Run the attack tree lens against the handful of goals, specific data, specific systems that would actually hurt if they were reached. Practically, start from a specific concrete goal, not a vague one. Exfiltrate this specific dataset or disrupt this specific service. Never just get hacked because a vague route produces a tree too broad to act on. Populate the leaf nodes from what you already have. STRIDE findings for the specific flaws. ATT&CK technique, names for the general methods an adversary would use to exploit them. Mark every and or relationship explicitly as you build outward from the root. This is the step teams skip under time pressure, and it's the step that makes the whole exercise useful rather than decorative. If you want to go further, assign a rough cost or likelihood estimate to each leaf: cheap and likely, expensive and unlikely. And you can roll those estimates up through the tree to find the cheapest complete path to the goal, which is very often the path worth defending against first, whether or not it's the path anyone's actually tried yet. This doesn't need to be an enormous undertaking to be worthwhile. A tree built for one genuinely important goal, by the same small group that ran your STRIDE session, using an hour of the same meeting, produces something more useful than a much larger exercise attempted for every conceivable goal at once. Pick the 2 or 3 goals that would actually be catastrophic if reached, build a tree for each, and treat the rest of the system's risk as adequately covered by the STRIDE findings on their own. 3 mistakes recur. First, building a tree once and treating it as historical documentation rather than a living artifact. The tree needs revisiting every time the architecture changes, exactly like the STRIDE session it draws from. Second, building trees only for goals an attacker has already attempted, and ignoring branches that remain fully open simply because nobody's used them yet. Kestrel's public-facing application path was real and available the entire time, whether or not it was the one actually exploited. Third, skipping the and/or discipline and just listing possible bad outcomes in a flat structure, which quietly turns the tree back into the same undifferentiated findings list STRIDE already produced, losing exactly the prioritization value that justified building a tree in the first place. We've now used 3 different lenses on the same 6 weeks at Kestrel: ATT&CK's stage catalog, STRIDE's per boundary flaws, and the attack tree's goal-specific paths. All 3 work at the level of a single system and a single set of techniques. There's a level above all of them we haven't touched yet, which broader security architecture practice actually makes sure this kind of analysis happens on a schedule, gets funded, and gets embedded into how an organization designs systems in the first place, rather than depending on one team's diligence or waiting for a 6-week intrusion to force the issue. That's next episode, and it's also where this season reconnects directly with the TOGAF season. If you're building systems that need to survive being breached, not just avoid it, subscribe, and I'll see you in the next one.